Imagine the universe. We live on a planet, orbiting a star. This star resides in a vast galaxy, one of countless others scattered throughout the cosmos. Zooming in, we find atoms, the building blocks of our world. Within these atoms lies a bustling, energetic realm, the realm of electrons. Electrons, those tiny particles of negative charge, are in constant motion, swirling around the atom's nucleus like planets around a sun. To understand the behavior of electrons, we use a powerful model called electronic structure. This information is crucial for understanding how atoms interact, form bonds, and ultimately create the molecules that make up our world. To navigate the intricate subatomic world of electrons, we use a sophisticated system of coordinates known as quantum numbers. These numbers are essential for understanding the behavior and properties of electrons within an atom. These quantum numbers, derived from complex mathematical equations, provide a unique set of identifiers for each electron within an atom. They help us determine the electron's position, energy, and other critical characteristics. There are three main quantum numbers we use to pinpoint an electron's location and energy levels within an atom. The principal quantum number, n, which indicates the electron's energy level and distance from the nucleus. The angular momentum quantum number, L, which describes the shape of the electron's orbital, and the magnetic quantum number, ml, which specifies the orientation of the orbital in space. Each quantum number provides a specific piece of information about the electron's state, helping us understand its behavior and interactions with other particles. Much like latitude, longitude, and altitude tell us the precise location of a city on Earth, quantum numbers give us a detailed map of the electron's position and energy within an atom. By understanding these quantum numbers, we gain a powerful tool for predicting and explaining the properties and behaviors of atoms and molecules, enabling advancements in fields like chemistry, physics, and material science. The principal quantum number, denoted by the letter n, is like the electron's energy address. It determines the electron's energy level. Imagine an apartment building where each floor represents a different energy level. The higher the floor, the greater the energy. Similarly, in an atom, electrons with higher n values occupy higher energy levels farther away from the nucleus. The lowest energy level, n equals 1, is called the ground state. When an atom absorbs energy, an electron can jump to a higher energy level, moving farther away from the nucleus. Conversely, when an electron loses energy, it drops to a lower energy level, like moving down to a lower floor. While the principal quantum number tells us an electron's energy level, it doesn't give us the full picture. The angular momentum quantum number, denoted by the letter L, reveals the shape of the region an electron occupies within that energy level. This is crucial for understanding the electron's behavior. These regions are called atomic orbitals, and they come in various shapes and sizes. Think of orbitals as electron clouds, regions of space where there's a high probability of finding an electron. These clouds are not fixed paths, but rather areas where electrons are likely to be found. Each L value corresponds to a specific orbital shape, and these shapes are fundamental to the structure of atoms. For instance, when L equals 0, we have an s orbital, which is spherical in shape. When L equals 1, the orbital is a p orbital, which has a dumbbell shape. When L equals 2, we get d orbitals, which have more complex shapes, often resembling clover leaves. And when L equals 3, we have f orbitals, which are even more complex and intricate in their shapes. Each orbital shape has a different energy and spatial orientation, influencing how electrons interact with each other and with other atoms. This interaction is key to the formation of molecules and the properties of materials. Within each electron shell, there are sublevels, each corresponding to a different L value. These sublevels are defined by their unique L values, which determine the shape and type of orbitals they contain. The number of orbitals within a sublevel determines the maximum number of electrons it can hold. For example, an s sublevel can hold up to 2 electrons, while a p sublevel can hold up to 6. Understanding the angular momentum quantum number and its connection to orbital shapes is crucial for comprehending the three-dimensional nature of atoms and how they form chemical bonds. This knowledge is foundational for fields ranging from chemistry to materials science. The magnetic quantum number, ml, orbital orientation in space. The magnetic quantum number, denoted as ml, adds another layer of detail to our understanding of electron location. It specifies the orientation of an orbital in space. Imagine our apartment building again. This time, each apartment represents an individual orbital within a sublevel. The ml value depends on the L value. It can take on integer values ranging from -L to +L, including 0. For example, if L equals 1, which is a p orbital, then ml can be -1, 0, or +1. Each unique combination of n, L, and ml defines a specific atomic orbital. Visualizing electron homes atomic orbitals. Atomic orbitals are not physical objects like planets orbiting a star. Instead, they represent probability distributions. They tell us the likelihood of finding an electron at a particular point in space around the nucleus. Imagine a map of a city with different colors representing population density. Regions with higher color intensity indicate a higher probability of finding people. Similarly, atomic orbitals depict regions around the nucleus where the probability of finding an electron is high. The shape of an atomic orbital is determined by the angular momentum quantum number, L, as we discussed earlier. Unveiling the secrets of s orbitals. The simplest type of atomic orbital is the s orbital, designated by L equals 0. S orbitals are spherical, meaning they have the same shape in all directions from the nucleus. Imagine a balloon inflated around a tiny point at its center. The balloon surface represents the region where there's a high probability of finding an electron in an s orbital. As the principal quantum number, n, increases, the size of the s orbital also increases. Each s orbital can hold a maximum of 2 electrons according to the Pauli exclusion principle. The spherical shape of s orbitals has important implications for chemical bonding. Exploring the intricacies of p orbitals. P orbitals, designated by L equals 1, are dumbbell-shaped, with 2 lobes on opposite sides of the nucleus. Imagine 2 balloons tied together at their ends, with the knot representing the nucleus. Each lobe represents a region where there's a high probability of finding an electron. There are 3 p orbitals for each energy level from n equals 2 and above. These 3 p orbitals are oriented perpendicular to each other, aligning along the x, y, and z axes. Each p orbital can hold a maximum of 2 electrons with opposite spins. The dumbbell shape of p orbitals leads to directional bonding. And navigating the complexities of d orbitals. D orbitals, designated by the azimuthal quantum number L equals 2, have more complex shapes than the simpler s and p orbitals. These shapes are not just abstract concepts, but are crucial for understanding the behavior of electrons in atoms. There are 5 distinct d orbitals for each energy level starting from n equals 3 and extending to higher energy levels. These orbitals are named dxy, dyes, dxz, dx2y2, and dz2. 4 of the 5 d orbitals have 4 lobes each, resembling a 4-leaf clover, which are oriented in different planes around the nucleus. The 5th d orbital, known as dz2, has a unique shape with 2 lobes along the z-axis and a distinctive ring-like shape around the center, adding to the complexity. The complex shapes of d orbitals arise from the more intricate solutions to the Schrödinger equation, which describes electron behavior at these higher energy levels. These solutions involve complex mathematical functions and symmetries. These unique shapes are crucial for understanding the properties of transition metals, which have electrons occupying d orbitals. Transition metals are found in the center of the periodic table and are known for their ability to form various oxidation states. Each d orbital can hold a maximum of 2 electrons with opposite spins following the Pauli exclusion principle. This principle states that no 2 electrons can have the same set of quantum numbers. The unique shapes and orientations of d orbitals contribute significantly to the rich and diverse chemistry of transition metals. These orbitals play a key role in the formation of complex compounds and the catalytic properties of these metals. Nodes unveiling the silent zones within atoms. Within the seemingly chaotic world of electrons, there exist regions of perfect stillness, nodes. Nodes are points in space within an atom where the probability of finding an electron is 0. Imagine a vibrating guitar string. The points on the string that remain stationary while the rest vibrates are nodes. Similarly, within an atomic orbital, nodes represent regions where the electron wave interferes destructively, resulting in zero electron density. The number of nodes in an orbital increases with increasing energy level. Nodes play a crucial role in shaping the properties of atoms and molecules. The significance of electronic structure. A universe within. The concept of electronic structure is far more than just a theoretical framework. It's the bedrock upon which our understanding of chemistry truly rests. By unraveling the arrangement of electrons within atoms, we gain insights into why elements behave the way they do, how chemical bonds form, and how molecules interact to create the diversity of matter we observe. Electronic structure governs a vast array of chemical and physical properties. Understanding electronic structure allows us to predict how substances will behave under different conditions and to design new materials with tailored properties. But before we part ways, let's take a moment to reflect on the ripple effect of understanding electronic structure. When we delve into the quantum world, we don't just uncover the secrets of atoms. We lay the foundation for groundbreaking advancements in technology, medicine, and environmental science. Think about the development of semiconductors that power our devices, the creation of new pharmaceuticals that save lives, and the innovative materials that make our world more sustainable. These all stem from our grasp of electronic structure. In every electron's dance, there's the potential for discovery. In every orbital's shape, there's a story waiting to be told. And in every quantum number, there's a universe of possibilities. So, as you continue your quest for knowledge, remember that each piece of understanding contributes to a larger tapestry of human progress. Stay curious, keep exploring, and never underestimate the power of understanding the unseen. Until next time, have a nice night, and be sure to have a good night.